Masha is great that she has being recorded.
Thank you again for the introduction. Let me just start sharing my PowerPoint. Let me know if you can see my introductory slide. Can you see this?
Yes.
Okay, perfect. So I want to thank Ken for organizing the summer EPS series and all of you tuning in. I'm currently in my office at EPS, and there's only myself. It's empty as usual during summer. It's only Jim Wright in his office. But I hope the EPS Wi-Fi will work well, and we won't lose connection. The title of my talk is Results from the Medford Auger Project PETM Drilling. But apart from my new data, I decided to expand this and give you an overview of research that was done on the PETM at Rutgers in the past 20 years. I summarized it to show that New Jersey provides best PETM records for various research, and also to highlight the importance of the New Jersey course to advance our knowledge about the PETM. I know a lot of you who have been in the department for a long time are familiar with the PETM, but in the last few years, we had a good number of students and faculty join Rutgers who might not be aware of what we've been up to in those recent years. For those in the audience not familiar with this major Cenozoic climate perturbation, I want to give a short intro. The Paleocene-Eocene thermal maximum, or the PETM, was an abrupt warming event initiated at the beginning of the Eocene 56 million years ago and characterized by a global temperature increase of about 4 to 8 Celsius degrees. Here I show the first records of carbon and oxygen isotopes of foraminifera from the ODP site 690 in the Weddell Sea. This paper, published by Canada and Stott in Nature in 1991, gave rise to the extensive research on the PETM for almost 30 years. These records show warming, which is indicated here on the right by the decrease in oxygen isotopes, and associated carbon isotopic excursion, or the CIE, represented by a decrease in delta C13 values. Here's the CIE recorded by foraminifera, but later on, the CIE was detected globally in both marine and terrestrial environments. And here I show you the paper that was published a year after the initial Canada and Stott's 1991. The delta C13 in mammalian tooth enamel also shows the CIE. Here's another records where that showed the CIE measured in soil carbonate nodules, and the CIE was also detected by the delta C13 records of total organic carbon, and here's the record from Spitsbergen. So all of the marine and terrestrial records sections show the CIE, on average 2.75 per mil in the deep sea and up to 7 per mil on land, which would require a substantial addition of light carbon into global reservoirs. The onset of the CIE was used by Marie-Pierre Aubry and her colleagues to correlate the Paleocene-Eocene boundary stratotype in Egypt. And the success of using the CIE for global correlations of the Paleocene-Eocene boundary was later reiterated by this paper in episodes by Ken Miller and Jim Wright. Here's the bulk carbonate record from ODP 690 that shows the CIE, the subdivision of the CIE into stages. There is this initiation of the decrease in delta C13 values that is termed the CIE onset, a period of stable low delta C13 values that is termed the CIE core or CIE body, and the exponential recovery to near pre-CIE values that is called the CIE recovery. Based on astrochronology, the entire duration of the CIE from its onset till the end of the recovery is approximately 200,000 years. And despite almost 30 years of the research that was done on the PETM, there is still important questions and important issues being unresolved. And among them are how fast the planet got into this global warming, or what was the timing of the CIE onset, and what triggered this warming and produced the CIE, or in other words, what was the mechanism of the PETM. And there are many mechanisms that have been suggested as triggers for the PETM. Here I show you the most popular hypothesis. The dominant hypothesis is dissociation of methane hydrates, although that is being challenged recently by both volcanism in the North Atlantic igneous province and cometary impact. One of the pieces of evidence favoring gas hydrates is that there have been reports that temperature leads the carbon isotopic excursion in course from New Jersey coastal plain. And I will directly address it in my talk in the second half. The majority of the PETM marine records...
Excuse me, Masha?
Yes.
This is Paul. Approximately how many gigatons of light carbon has to be produced to,
if it's methane, if it's methane, it's approximately 2,500.
Okay, and if it's a volcanism?
If it's volcanism, depends on if it's just CO2 or if it's the intrusion of the intrusion that went through the materials that are high in organic carbon. So if it's just CO2 with -5, I think, I don't want to lie, but it's something about 90,000. I don't remember that, but it's a really large number.
Okay, thank you.
Sure. By the way, if you have any questions, feel free to interrupt me during the talk. So the majority of the PETM records, marine PETM records, come from open ocean cores that are condensed and very thin. So here's Jim Zakos from Santa Cruz holding one of the cores that was recovered from the Walvis Ridge. Over here, though, these cores were drilled as a part of Lag 208 in the South Atlantic. And you can see this sharp contrast between the Paleocene and Eocene sediments and thin PETM records that are less than 1 meter in thickness. In contrast to open ocean cores, stratigraphically more complete in regards to the CIE onset and core, and much thicker, up to 11 meters marine PETM sections, are found along continental margins, specifically on the New Jersey coastal plain. And here's the correlation of this classic records that I showed previously from the ODP 690 to the cores from New Jersey Paleo Shelf, showing the relative thickness of the CIE core of 1 meter in ODP 690 and thick CIE core from New Jersey cores. An advantage of the New Jersey Paleo Shelf is its location on a passive margin with relatively high sedimentation rates, resulting in thick sections and thus higher CIE resolution. Also, location on the passive margin with relatively stable tectonics allows paleo water depth reconstruction for the sites that were drilled on the New Jersey coastal plain. And finally, the Paleocene-Eocene boundary in New Jersey is accompanied by a lithological change from silts and sands to clay. And here's the split course from Medford, where you can see this transition. Such clay silt-rich lithology acts as a barrier to interaction of pore water with carbonate, providing excellent preservation of foraminifera that mainly used in past climate reconstruction. And here are photographs and ECM images of both planktonic and benthic foraminifera from the onset section at Medford course, showing their well preservation. As a result, the New Jersey is the only location in the world, beside other section in the Salisbury embayment, that not only have the PETM recorded at high resolution, but also contain both inorganic carbon in form of carbonate and organic carbon, allowing multi-proxy studies of the PETM. And now I would like to give you a brief history of the PETM research that was done at Rutgers using cores drilled in New Jersey. And this map shows you most of the cores that were used for studies of the PETM. The very first core was drilled in 1998 at Bass River State Park over here. And it was the first PETM record that was published from the New Jersey coastal plain by Ben Kramer, showing stable oxygen and carbon isotopes measured in benthic foraminifera. After that, 4 years later, Dennis Scant published a paper where he studied magnetic properties of this Marlborough clay, a very unusual unit that records the PETM on the New Jersey coastal plain. Dennis and his co-authors suggested, by studying the magnetic properties of the Marlborough clay, they suggested a cometary impact that produced this clay and ejecta. After that, Jim Wright and Morgan Scheller continued studying this very unusual clay. They looked at the layers that they found in this clays and did a high-resolution measurement of oxygen and carbon isotopes as well as percent carbonate. They suggested that the deposition of this couplets should represent annual deposition. And what they found is that the different response in percent carbonate and delta C13 values. There was a very sharp drop in percent carbonate that appeared within one couplet, and there was a more gradual decrease in delta C13 values that appeared in couplets. And such annual forcing that was for the couplets that was suggested by Jim and Morgan matches the observed changes in the modern ocean with respect to the rates of the CO2 invasion of less than 1 year and carbon isotopic equilibrium of approximately 1 decade. This study brought a lot of controversy because it suggested a instantaneous release of light carbon and supported the hypothesis of the cometary impact. And 3 years later, Morgan Scheller and his colleagues found a physical evidence of the impact. They found this microtectile spherules right at the onset of the CIE. And these graphs over here show the concentration of the number of spherules per gram, and you see the peak of the concentration right at the onset of the PETM. So that was a physical evidence for the impact from the New Jersey coastal plains. And a couple years later, Megan Fung, who was working with Morgan, who was a PhD student of Mimikatz, studied New Jersey cores as well and found charcoal in the layer of the in layers of the Marlborough clay, and suggested widespread in intense wildfires that were associated with the PETM. Very interestingly, Dennis Scant and his colleagues a couple years before published a paper where they also suggested that there was wildfires, and the enhanced magnetic properties of the Marlborough clay is the product of soil pyrogenesis. So besides all this very interesting research on the talking about the various triggers and the timing of the PETM onset, there was also a number of research looking at the actual deposition of this mud on the shelf. And here's Bob Kopp standing on the outcrop in Virginia, right on top of the Marlborough clay. He studied magnetic. magnetic properties and looked at the distribution of the magnetotactic bacteria. So he separated it on different phases, and by the distribution of these phases, concluded that there was a development of the large tropical river system on the mid-Atlantic margin, which is similar to the modern Amazon shelf. And following this study, Luca later looked at the distribution of this mud and how the CIE is recorded in each of the sites by this duration and thickness of different phases of the CIE, onset, CIE core, and CIE recovery. He proposed the cliniform depositional model, where in more proximal sites that are closer to the mud source, there will be a thicker initial phases of the CIE, whereas the sites that are further offshore will record the later phases of the CIE at higher resolution. And since I said that New Jersey cores also contain well-preserved foraminifera, there were a number of studies that were done on nanofossils and foraminifera. And here's one of the studies that was published in 2004 by Alicia Kahn, who was a PhD student of Marie-Pierre Aubry, who detected this very unusual nanofossil assemblage, which is called RD, that was associated with the PETM. And I also studied foraminifera, and I discussed isotopic trends in both planktonic and benthic foraminifera, and concluded in the paper that was published in 2017 that there was either a weakened thermocline associated with the onset of the PETM or change in the season of calcification in order to explain different isotopic responses of benthic and planktonic foraminifera. And Wayman C. and Marie-Pierre further explored the vital effects of foraminifera and also did studies of the ecological adaptation of the foraminifera that has symbionts, algae symbionts. And besides stable isotopes, forams were also used to measure trace elemental ratios at the Ayers lab. And here's the paper that was published in 2016 by Tali Babila, former Yayer's PhD student, who measured magnesium calcium and boron calcium in foraminifera. And Tali estimated approximately 0.4 pH unit decrease in the in surface ocean pH, and gave a perspective on the ocean acidification during the PETM. So this is not all of the papers that were published by research group at Rutgers on the PETM course. And there are so many more papers that were published on New Jersey course by researchers from all across the world. But I just wanted to give you various flavor of the research that was done in the PETM here at Rutgers in the last 20 years. And now, finally, let's move to Medford, New Jersey. Luca Pedreca, in his paper, which is currently in review in geology, discussed distribution of different portions of the CIE at 4 sites across the New Jersey coastal plain. Here's the location map on the right, with the sites projected on the paleoslope profile. And to the left, you can see the bulk sediment carbon isotopic records of these sites. The variability of the CIE records across the paleo shelf can be explained by the cliniform progradation of fluid muds, which is similar to Amazon shelf today. And based on this depositional model, the most proximal to the mud source location should preserve thicker sections of recording the initial part of the CIE. And the sections further offshore should record thicker intervals of the later phases of the CIE. If such, most up-deep cores from the proximal location in Medford site should recover the thickest PETM onset. Why is it important? Expanded sections of the onset can provide us a clue on the trigger mechanism. And this is why I chose Medford to constrain lead-lag relationship between the CIE, warming, and associated environmental changes, which was the main goal of this study that I'm going to show you. Medford Auger Project, or MAP, drilled 6 sites and total 9 cores down deep of the Marlborough clay outcrop in Medford, New Jersey in August 2016. Here I show you the location of Medford in relation to other New Jersey coastal plain sites and the location of the 6 sites relatively to each other. Here's the drilling truck that we used to auger drill of this course, and the photographs that I showed you before. That was the only day where I helped to recover the course and to document them. And this profile shows the thickness of the Marlborough Formation in each of the sites and their relative position in regards to the elevation. I studied 2 cores from most down deep and the deepest site 3, cores MAP3A and 3B. These are sister cores that were drilled right next to each other. And here's the photographs of this course. So let's start with the first looking at the lithology that was recovered in this course. Here's the percent course fraction of these 2 cores, showing lithological change across the PETM from glauconitic sands of the Vincenttown Formation to kaolinitic clays of the Marlborough Formation. And this course recovered 60 centimeters thick interval, recording a gradual transition from sands to clays. Although this transitional unit is disrupted by the core break at MAP3A, this is what I'm showing here, the zoom to the core photographs on the left. In MAP3B, it is clearly not disturbed, showing a gradual exponential decrease in course fraction from 70 to 1%. The PETM at Medford is also associated with a steady 3.5 per mil decrease in bulk delta C13 values. These are the carbon isotopic records from Luca Pedreca. This gradual change in bulk delta C13 values appears within 50 centimeters and is not a result of the drilling disturbance. Here again, I'm showing you this zoom into the course and the intervals within which this delta C13 decrease was detected. And this is the summary figure showing all of the bulk sediment characteristics that were measured in both cores. The percent course fraction on the left, then percent carbonate that shows drop in carbonate content associated with the PETM onset, the bulk sediment delta C13 in red, and delta C13 of organic matter that are measured with Linda Godfrey here at Rutgers. In order to, since delta C13 decrease is gradual, I used not in bulk carbonate, I used not only bulk sediment record, but also total organic carbon in order to establish position of the delta C13 onset. And both organic and bulk sediment delta C13 records show this gradual decrease in delta C13 values. And I determined this gradual decrease as the CIE onset. And the sediments that are above this orange box over here are record the Eocene deposition, and the sediments that are below this orange box recorded the Paleocene deposition. In the next slide, I'm going to show you how I overlaid those records to show how this bulk and delta C13 records agree with each other. Here's the MAP3B, MAP3A, and in order to support the position of the CIE onset, I also measured delta C13 values in both planktonic and benthic foraminifera. And this gradual change in delta C13 values is not a result of the disturbance of the core. It appears within, there's no core breaks that correspond to this interval. The delta C13 bulk is also mimicked by both planktonic and benthic foraminifera, and this is not a result of the bioturbation and extensive mixing. And putting all these three records together from bulk sediment, organic carbon, and foraminifera, I indicated the expanded onset that indicated by this orange box within 20 and 30 centimeters thick interval. This is where the delta C13 values change across the Paleocene-Eocene boundary. Now, why did spend so much time talking about the position of the CIE onset at Medford cores? This is important. The placement of the CIE onset is important because the relationship between the CIE onset and warming is critical to evaluate mechanisms. Epi Slush from Utrecht University, who is an expert in dinoflagellates and organic geochemistry, studied environmental changes across the PETM onset in many locations. And here, the two records from New Jersey sites, Wilson Lake to the left and Bass River to the right. This paper used the organic paleothermometer Tex 86, which is based on the relative distribution of archaeal membrane lipids to estimate the temperature. And they also use the bulk sediment delta C13 values to place the CIE onset that they determined by this sharp inflection, sharp decrease in delta C13 values. Comparison of the two records, delta C13 of bulk and temperature from Tex 86, showed temperature leading the CIE onset. They suggested that this precursor warming triggered the dissociation of methane clathrides and thus supported the clathride hypothesis as the trigger of the PETM. However, reevaluation of this published records and application of the updated Tex-H calibration that uses more core tops disputed the temperature lead in Wilson Lake and in Bass River. This shaded region here that I show in orange represents intervals of initial changes in both temperature and delta C13 values prior to the main inflection in delta C13. And within this box, this shaded intervals, we can see that there is a concomitant changes in both temperature and delta C13 values. Questioning the thermal trigger at these locations. At Bass River, however, the temperature apparently still leads the delta C13 of the bulk, but when it is compared to delta C13 of the dinoflagellates, the changes in both records appear still at the same time. And it also should be noted that geochemical signals across the Paleocene-Eocene boundary at most distal Bass River site were possibly discontinuous due to truncation of the onset, a possibly short hiatus, and reworking. And since Medford cores recovered the thickest and most expanded CIE onset among the New Jersey coastal plain cores, I compared the high resolution delta C13 records with tax 86 temperature records in 2 cores. And this record on the right in purple is the temperature record from tax age calibration. And the comparison of the delta C13 and temperature record from tax 86 clearly shows no warming prior to the CIE onset, rejecting the precursor warming hypothesis. Tax also shows a total warming of 7 Celsius degrees. And interestingly, this warming occurs in 2 steps: the initial 5 Celsius degree warming that was followed by more gradual secondary warming of 2 Celsius degrees. And the step in the temperature entirely appears within this low carbonate zone with less than 1% calcium carbonate that is highlighted here by this blue box. MAP3A records are consistent with those from MAP3B and also show no warming prior to the CIE onset. And to confirm this, our own statistical expert, John Schmelz, applied a Gaussian process regression to cross-correlate delta C13 bulk and delta C13 organic with tax 86 temperature records in both cores. And here I'm showing a couple of the examples of these cross-correlations. The dots on these diagrams show the actual data points through which the regression analysis were ran. The bottom curve shows the cross-correlation of records and lead of one record in relation to another. The example on the left shows no lead lag between bulk and organic delta C13 record, suggesting simultaneous decreases in delta C13 values. The cross-correlation to the right shows the correlation between the delta C13 of bulk and tax 86 estimated records. And this correlation indicated that the warming and the CIE are coincident with 0 lag at 95% confidence interval. And finally, I want to show you the spatial distribution of the tax 86 record across the New Jersey Paleoshelf. Here's the 5 sites where the tax 86 was performed and their projection on the Paleoslope profile. And the records, the temperature records from all of this site. A spatial comparison revealed a larger warming of 7 to 8 Celsius degrees at proximal sites and 6 Celsius degrees warming at distal Millville and Bass River. And this is consistent with tax 86 variability on shelf today, with studies of modern core tops from South China Sea and Mediterranean that showed cooler tax 86 temperatures in nearshore environments than the satellite measured SST. Also, all of the sites recorded a more sharp initial warming and more gradual secondary warming that I'll show you in the following slides. John applied cross-correlation analysis to the other New Jersey coastal plate sites as well, and showed no temperature lead except for Bass River. Also, as I mentioned before, all New Jersey sites revealed this second warming. Here you can see the zoom in the top panel to the temperature records. The blue box here indicates the low carbonate interval, and all of the sites recorded this secondary warming that occurs within the low carbonate zone. The secondary warming also corresponds to decrease in coarse fraction. And here I overlay the tax record in each site with the percent coarse fraction that was measured in each. And just to let you know, for the coarse fraction, I use different scales, and not to confuse you. But nonetheless, in each of the sites, the secondary warming is corresponding, which is highlighted in green over here, is corresponding to a sharp decrease, not sharp, but to a decrease in the coarse fraction, implying that the warming was synchronous with the onset of the rapid clay deposition, and the secondary gradual warming might be an artifact of the increased sedimentation rates associated with the PETM onset. So here's the takeaways that I want you to have as a result of the studies that I did at Medford. Expanded section at Medford and other New Jersey coastal plain sites show no temperature lead to the CIE onset, calling into question a temperature trigger for carbon release. Tax 86 based temperature estimates show larger warming and more proximal sites than in more distal sites. And all New Jersey sites suggest that the warming occurred in 2 steps, although that might be an artifact of rapid clay deposition and increased sedimentation rate. And this is something that I want to explore in the near future. And I would like to finish my talk showing you the distribution of all tax records that were done in the PETM course. And to my surprise, there were very small number of tax 86 for the PETM. This dots over here show the location, and the table below indicates the papers that published this records. And half of this records, tax 86 records that were produced, were done in course from the New Jersey coastal plain. And I should tell you that those records are so far the best temperature records for the PETM that were produced in the entire sections from both marine, from both shelf and open ocean locations. Again, supporting the significance of the New Jersey coastal plain drilling and its impact on the PETM research. With that, since there was so many amazing data and great research questions, very intriguing research questions were done with course in New Jersey. Ken Miller, the master of drilling in New Jersey, and his PIs suggested a drilling in both New Jersey coastal plain and in the Delaware and Maryland coastal plains, because a lot of the cores that we currently have from New Jersey are depleted, and they were heavily sampled for various analysis. We proposed the sites that's shown here in blue to drill in New Jersey and in Delaware and Maryland to obtain more cores for more research on the PETM. And this proposal was funded, and the workshop to put together drilling proposal was originally scheduled for January 2021 to take place here at Rutgers, but because of the COVID situation, it was decided to be postponed till fall 2021, and more than a year. So stay tuned. There will be more exciting results, hopefully coming from New Jersey. And I really hope that a lot of research from around the world will be able to join this drilling proposal and put together the proposal to drill more sediments in New Jersey and Maryland, Delaware. And with that, I want to thank you for your attention and open up. I would like to open up this WebEx room for discussion and your questions.